Okay, you guys, we are just starting section 6.4. So we are going out of order and skipping 6.3 because we need to do some stuff on chain rule first in 6.4 before we can go back and hit 6.3. So you do need to do those the way the calendar says. And we're starting 6.4 to kind of finish out this week. And then next week, we will do the rest of 6.4. So it's kind of long. And again, the algebra is the killer, more probably so than the calculus. I mean, it takes a minute to get the calculus down, but the algebra with all of the spaces to make mistakes are where you guys tend to make the mistakes. So I kind of introduced this notation briefly to you on like the last example that we did in the last video, but take a minute in your notes and kind of write this down, that besides that prime notation where we just have the little tick mark, right, that we often use what is called derivative operator notation to indicate that we're doing differentiation. So if you have a function that's defined in function notation, like f of x equals the square root of x. Well, right now, that's not very calculus friendly because we don't have a rule to take the derivative of a square root. But we know if we just think about like pre-calc level concepts that the square root is the same as the 1/2 power, and we would switch our original function, this is still f of x, into a more calculus friendly form. Now it's really just the power rule. That's our favorite rule, right? We love the power rule. So when we're doing differentiation, now we're actually ready to take the derivative because now this is in a calculus friendly form. So the notation that you guys are going to see as you're going through homework and as we get ready to take our final test, a lot of times is going to be function notation, and the prime notation is the easiest, right? And now you're ready to take the derivative of both sides. So you're going to say f prime of x equals, we're going to pull that power down. We're going to leave the x as the big base alone, but we're going to decrease the power by 1. So 1/2 minus 1, so 1/2 minus 2/2 will give us negative 1/2. And then Hernie and I have both talked to you about how, hey, we're going to try and end in the notation we start in. And we didn't start with negative exponents, and usually negative exponents aren't so zesty anyways for the way to end a problem in algebra. The 2's already in the denominator, now our base x would flip down into the denominator, and that's what changes the negative 1/2 to a positive 1/2 power. And then our derivative, f prime of x, back into the radical notation would be 1/2 square roots of x. And if you haven't taken some time to kind of memorize that this turns into this, you might want to do that. It tends to show up quite often on a lot of problems in a lot of ways. So that's the prime notation that we're like kind of more familiar with. And that's going to feel like the easiest of all the notations, but that's not the only notation that you guys are going to see when you take your test. So instead of function notation, if I had said the rule is y equals the square root of x, and this is kind of what I showed the other day, right? You would change it into y equals x to the 1/2 power. So radical notation is not calculus friendly, but rational exponent notation is, because then the power rule applies. We have an x, a variable raised up to a power. It doesn't matter if the power is a positive number, a negative number, or a fraction. And now if I want to take the derivative, remember how I taught you this. I am taking the derivative of both sides of the equation with respect to x. So it'd be dy over dx, the derivative of y with respect to x equals. And this is where I'm applying the calculus. Here's where I'm taking the derivative using the power rule. And we would clean it up the same way we did last time. And I'm going to skip a couple of those steps and go straight to this simplified all the way version, 1/2 square roots of x. So we end in the notation that we start with. And sometimes you got to really read the directions. We'll ask you for dy over dx in operator notation, and sometimes we'll say y prime, and you can even have your tick mark on the y and write y prime. But then there's kind of like this other notation. So this d over dx, make sure and write this down in your notes and write down how to read it. You read this as the derivative of. But it's kind of like the abbreviation LIM for limits, like how we would say you have to take the limit of something. You have to take the derivative with respect to x of something. So this isn't when you have a function that's like defined as an equation with a left-hand side and a right-hand side. This would be where they would say d over dx of the square root of x. And you're taking the derivative with respect to x of this expression. So it's not necessarily defined as an equation with a left and right-hand side, but you still are trying to say, hey, we're doing this process called differentiation, right? So this derivative operator notation is trying to indicate, hey, you're going to take the derivative of whatever expression's inside of here. So right now, this expression maybe isn't, again, so calculus friendly, so we would change it into, hey, I'm trying to take the derivative with respect to x of the expression x to the 1/2 power. And this is like where people, probably the worst notation is from this one right here. So you guys like really need to pay extra special attention to this. So what happens when you're in this notation is you just write equals and you start taking the derivative. And that like throws people off because it's not as easy as when you're in function form and you're saying f prime equals this when you start taking the derivative. Or when you're in curve kind of form, whatever the letter is. Sometimes this is u and you write du over dx. Sometimes this could be a different letter like p and you could write dp over dx. Sometimes it might have a t on this side, so it might be dy over dt. But you have an equation still with a left and right hand side, and once it's calculus friendly, you take the derivative of both sides with respect to x. That's an easier operator notation. This is when it's taking the derivative of whatever the expression is. So once you're ready to take the derivative, you just write equals and you start stringing it out on the right hand side. So we would apply the power rule and we would bring the power down, we'd leave the x alone, we would decrease the power by 1, and then we would just keep working this down and clean it up algebra-wise. So flip that x down to the denominator to change the negative 1/2 into a positive 1/2, and then change back into radical notation. And I don't even care if you write this every single step of the way, because you're kind of saying the derivative of this expression turns into this final cleaned up answer. Okay?
And we don't really write it, but we really used it kind of back here. So like the step that we took the derivative in, like we could have written another step right there and said d dx of y is going to equal d dx of x to the 1/2. We just didn't really write that out and just went straight to dy dx.
Yeah, went straight to the
and
answers.
then we went straight to our derivative without actually writing the derivative with respect to x of x to the 1/2.
Okay? So all of those notations you're going to see as we do our test. So you need to feel comfortable with all of them. And I think especially in 6.3, they introduced that notation, but we're going slightly out of order. So we're kind of introducing the notation because it's used in 6.4. So if you see this notation, d over dx, and there's an expression here, then the idea is as long as you're ready to go, unless you maybe do one step to make it more calculus friendly, you just put an equal sign and you start taking the derivative and you clean it up that whole way through down the right hand side. If you have something that's more equation form where you have a left and you have a right hand side, then you just got to watch the directions. If they want you to use prime notation, which is usually when you're in function notation, great. That's what you're going to feel most comfortable with from section 6.2 anyways. And then if they want you to use the operator notation, but you have something defined on the left, then it's the derivative of that letter with respect to x, and then you start taking the derivative on the other side. Okay? So we had to talk about notation before we even got to chain rule. So there's kind of the stuff on notation, and now let's talk about the chain rule. So chain rule is pretty exciting. Whenever we get to the chain rule in calculus, we always tell them it is the most tested derivative rule on the AP exam. So I mean, you have all of these other rules, and I'm not saying they don't have valid points, but the chain rule is kind of the most tested rule in all of calculus. And that's what we're going to spend a whole bunch of time on. And of course, if you miss it when it needs to be applied, you're going to miss a ton of points. So you got to recognize how to see it. So the chain rule is what we use to differentiate compositions of functions. Compositions of functions. So remember when a couple different times this year we have like decomposed functions, so you recognize like the inside piece and the outside piece. That's why we kept doing that, was for when we got to chain rule. So if you have a distinct inside and outside piece that you could kind of decompose and go, oh, if I made this my f of x inside piece and I made this my g of x outside piece and I composed them g of f of x, I would get back to the more complicated rule. That's when you have a composition of functions. And that's where chain rule needs to be applied. So the main thing about chain rule is we say it in words before we like really learn how to use it. And we're like teaching it at a really like basic level in pre-calc. You'll learn way more with this. And when it gets way more complicated when you get to calculus next year. Okay, so the main thing is if you know how to do it in words, then I feel like you understand it. So in words, the chain rule is the derivative of the outside I don't think there's any fancy song to sing with this one. Sorry, guys. The derivative of the outside, leaving the inside unchanged, or some people say leaving the inside alone.
Inside stays the same.
Or the inside stays the same, times the derivative of the inside. Which is why I was saying you got to be able to notice and see this distinct inside and outside, because you're like taking the derivative of the outside, you leave the inside remaining the same expression, but then you're multiplying it by the derivative of the inside. So again, the notation can get like a little bit kind of messy, but if I show you this first, because the prime notation is probably what we're most comfortable with. So if I define, just like a general idea, h of x as a composition of functions. Let's do it the Fogg way, f of g of x. Remember on composition we work inside out, right? So this is f open circle g of x, the Fogg way. And then if I said, okay, find h prime of x. Well, we could use a little tick mark. That's a notation we probably feel the most comfortable in. And we would take the derivative of the left-hand side because we have a left and right to work with. And the derivative of h of x is the h prime of x. But because this is not a product, these are not f of x times g of x. It's not product rule. It's not a quotient. I don't have a fraction bar or division bar. So it's not quotient rule. It's not power rule. It's really a composition. It's two things composed inside of each other. The f is like the outside and the g is like the inside. So don't you see that distinct inside-outside idea? So what the chain rule says is take the derivative of the outside. Well, the only way right now I can do anything is just with showing it in the function notation. So it's f prime, leaving the inside unchanged. Okay, leave g of x the same, g of x, leave it alone, times the derivative of the inside. So the inside was g of x, so it's times g prime of x. And that's the easiest probably notation to show and understand with chain rule. It's trying to say the same thing that we're saying up here in words. So that's kind of one notation. Using that operator notation, if we said take the derivative with respect to x of f of u. So this is like an expression that just happens to be a function. So remember, if it's this notation and we don't have like a left and a right, we just start taking the derivative, right? So I'm just exposing you to another notation. This is a notation we usually show a lot in calculus and that the calculus kids have on their time test. But this is just another notation. You would take the derivative of the outside, which would be f prime, leaving the inside unchanged. Okay, leave it as u. But then you would have to multiply it by the derivative of the inside. So the derivative of the inside would be du over dx. The derivative of u with respect to x. So this is like the derivative of the outside, leaving the u the same, leaving the inside the same, times the derivative of the inside. It's just a different notation to show the chain rule in a different way. And really for tonight, what you're going to be working with the most on homework is using the chain rule when you think about things raised to a power. So if we wrote down again just our general power rule that we learned back when we first appreciated definition of derivative in 6.1 and then started doing our shortcut rules back when we were doing the beginning of section 6.2, right? We said, okay, if we have some function f of x and it equals some variable x raised to a power, it doesn't matter whether that power is a positive number or a negative number or a fraction. That's how we were changing radical notation to work with derivatives, right? Changing them into rational exponents, into fraction exponents. And we took the derivative, didn't we bring the power down, and then we left the x the same, and we decreased the power by 1, right? That was the power rule when we're doing first semester calculus or differential calculus. Well, now we're just kind of expanding that idea where if we have a whole expression, a whole quantity raised to a power, some inside something, that might just be a single x, and I want to take the derivative of it, right? I still would bring the power down in front. I'm just writing it in words. I'd leave the inside alone. I'd still decrease the power by 1, so the power minus 1. But then I'd have to multiply, sorry, I'm on the edge of the board, by the derivative of the inside. So it's just a whole quantity raised to a power instead of maybe like a single variable raised to the power. And if you can get your head wrapped around that part of the chain rule, then that's a really good step into calculus for next year, okay? So now we've kind of like gone over some notation, gone over how to say it in words. The chain rule is theorem 5. Remember the theorems in our packet are numbered, which is kind of how it is in our calculus book too. So if you want to write down that, that's theorem 5. But the more important thing is you need to know how to say it in words. Just like you kind of have learned with the product rule and the low D high stuff for the quotient rule. Oh, the derivative of the outside leaving the inside the same or alone or unchanged, however you want to say that, times the derivative of the inside. So we're going to go through some examples, and Hernay and I are going to kind of bounce back and forth from being up here on the board presenting examples, and this is going to match your homework to finish out the week. And then of course it gets harder because we'll have some section 6.4 stuff next week. So you guys, you won't turn this in until next week. You're just starting it for part 1 for today. So we want to find each derivative, and we're going to start with this. U of x equals x cubed minus 6x plus 1 to the 10th. So as we're going through these examples, there's a lot of particular things we're saying. Not just the calculus, but a lot of the end part of the problem with the algebra. So like you need to pay close attention to both. So if I said, okay, find the derivative of this, if it were individual terms, one right after the next, all going down in descending order as a polynomial, we'd be fine. We just take the derivative of each piece. Calculus is beautiful like that. But that's not what it is. It's this whole cubic quantity raised to the 10th power. And then a lot of kids will say, oh my gosh, are we supposed to like write that out 10 times and multiply it all by itself 10 times in a row? So then it's individual pieces and then you can take the derivative? Well, no, that doesn't seem very efficient, which is why we have, the chain rule. So do you guys see that this is like a whole something to a power? And we have this distinct inside and outside piece. So the inside is the x cubed minus 6x plus 1. Usually there's some sort of like grouping symbol that gives you like the light bulb that it's the inside, whether it's parentheses or brackets or a radical, what's underneath the radical called the radicand. A radical is like a grouping symbol. Absolute value bars are like a grouping symbol, like something that like usually distinguishes the inside. And then the outside is that the whole thing is being raised to the 10th. And a lot of times what I'll tell kids when we first start this is I'll say, okay, well, if I gave you x to the 10th, what would you do to take the derivative? Oh, I'd bring the 10 down in front, I'd decrease the power by 1, so it'd be 10x to the 9th. Well, the idea of it's the same. I'm taking the derivative, so this one was function notation, so we're like, yay, it's our favorite. It's just not f or g, it's u, so it's u prime of x equals, I bring the 10 down in front. I still am going to decrease the power by 1, and now the whole thing's going to be to the 9th, but the idea is what I have is still that inside cubic. So instead of it being a single variable x, it's like this whole quantity. So this is the derivative of the outside, 10 times x cubed minus 6x plus 1 to the 9th, leaving the inside unchanged, times the derivative of the inside. Well, now the inside is just a polynomial, one term right after the next. So can't we just take the derivative of each piece, one right after the next, using power rule? And it's really power rule and the constant multiple rule and sum and difference rule, but you guys just lump all those together and say power rule. So isn't the derivative of x cubed, it's going to decrease by power, turn into 3x squared, right? That makes sense. A cubic drops down to a quadratic. Isn't the derivative of negative 6x just going to be negative 6? This is x to the first power. 1 times the coefficient in front would stay negative 6. When you decrease the power by 1, it's x to the 0, which is just an understood 1. Plus this is linear, so you're dropping down to a constant. And Mr. Hernay, what's the derivative of positive 1?
0.
0, because the derivative of constant is 0. Right? The slope of a constant horizontal line is always going to be 0 slope. But this is what you guys want to do every time. And that is wrong. And you would miss points every time. So yes, that's multiplied by the derivative of the inside, because the way it's written right now, it's 10 times this whole quantity to the 9th, and that whole stuff is just times the 3x squared, and it's like this minus 6 is way at the end. Subtracting 6 at the end, and that's not what you mean. Times the derivative of the inside. Well, if the inside derivative is more than one term, you have to have grouping symbols there. You have to keep the grouping symbols there. So if this did not have parentheses, it is false. It is incorrect, and you will miss points. The only thing, because a lot of times you guys want to do more, like you want to go farther than what's needed, the calculus is done, and the only thing to really clean it up algebra-wise is sometimes with our derivative, when it's all multiplied as a product, we will just put it in what we call ascending order. So any monomial pieces you move in front. So I move the 10 and keep it in front. This quantity is only to the first, so I might string that quantity next, because if I'm thinking ascending order, I would be going up in power. That's to the first power. And this quantity is to the ninth. X cubed minus 6x plus 1, the whole thing to the ninth. I would give you full credit either way, but that is just one way to write a really nice answer for u prime of x. You aren't going to really multiply this out by itself 9 times in a row, so we just leave it in factored form. It's fine. Some people will go, well, don't you want to distribute the 10 in because this is 10 and this quantity is not to anything except the first, so you can distribute? And the answer is, I'd be cautious of that. If you want to do that, okay, more power, rock on with your bad boy self. And 10 times 3x squared would be 30x squared, and 10 times negative 6 would be negative 60. But if you do not have this in parentheses, now it's wrong, because it would be both of those terms times x cubed minus 6x plus 1 to the ninth. So to avoid like trying to do too much multiplying and then lose it because you have bad notation, I would just leave it here. Okay? So there's your first example. I'm going to erase that version, but this would be acceptable. This one's just better. So next one, letter B. We have y equals, so again, here we have like actual equations with a left-hand side and a right-hand side. Y equals the square root of 1 plus x squared. So all of that 1 plus x squared is underneath our radical, and the directions say find dy over dx. So if we're particularly telling you what kind of notation you need to use, you need to follow those rules. I didn't say find y prime with the tick mark. I'm using that operator notation. I'm really taking the derivative of both sides with respect to x in what we call operator notation. So the derivative of y with respect to x, maybe skipping that like little step Mr. Herney showed you that we don't typically write down. They kind of showed you that step in blue. We'll just go straight to dy over dx. The derivative of y with respect to x. And some of you might go, uh-oh, though, I don't know what to do with the square root. So if I wanted to, if I thought about making this more calculus friendly, isn't y equals the square root of 1 plus x squared really the same as y equals, it's still my function y, all of 1 plus x squared, the whole thing to the 1/2 power. So rational exponent notation, which I know you guys don't get a lot of practice on coming up through integrated curriculum, rational exponent notation is calculus friendly. Radical notation is not calculus friendly. You might go back to it, you might simplify with it, but you can't take derivatives with it. And now it's maybe even more like of an aha moment that there's an inside-outside piece. We have this composition of functions. Hopefully you recognize this as the inside piece even if you have the square root attached on the outside of the whole thing.
Another thing students do in the past is they say this is y, then dy dx. But then over here, they say dy dx equals 1 plus x squared to the 1/2, and dy dx does not equal that. Y equals 1 plus x squared to the 1/2. Okay, so just be careful that whenever you do take the derivative on one side, you have to do that at the same time on the other side.
Like that whole idea of keeping the equation in balance. So that's why I kind of went up here and just did like this extra scratch work on the original y equation. So now I'm ready to take the derivative of both sides at the same time. So if I have something raised to a power, it's okay if it's not a single x. The power rule still applies. We're just kind of expanding the general power rule into this chain rule idea. Or we're going to still bring the power down. We're going to keep it inside the same. We're still going to do the power minus 1, right? Decrease the power with 1. But then we have to multiply with the derivative of the inside. And I think a lot of you could probably see that kids would bring the power 1/2 down. They would keep the inside unchanged, so it's still 1 plus x squared. What the radicand was before is still the same thing. They would decrease the power by 1. 1/2 minus 1 would turn into negative 1/2, and a lot of kids will stop right there. But then you haven't completed chain rule. You took the derivative outside, you left the inside unchanged, right? Just like Herney kept like saying, I lost my place, I need to say low d high minus high d low all over the square below. Like you got to say it in words. I took the derivative outside, I left the inside unchanged, I decreased my power by 1 to finish taking the derivative outside, but now I need to multiply by the derivative of the inside. So the derivative of 1, oh, that's another constant that goes to 0. The derivative of positive x squared, we'd bring the power down, and it would become 2 times x to the first power, and we probably wouldn't even write the x to the first power, we would just write times 2x. Now in this problem, if you didn't put parentheses, it's okay. This is just one term. If this is just one term, monomial piece, you don't have to have parentheses there. But if it's more than one term, the parentheses have to be there. So I was kind of saying this on the last example from the last video. I feel like rational exponents, because you guys haven't used them a lot, throw you for a loop. And typically kids will finish better if they change back into radical notation. So this is your step of calculus. And every other step I do past here is going to be the algebra cleanup. You get points for both. You got to be able to do both. So I'm still trying to find my derivative of y with respect to x. I'm just trying to like clean it up a little bit, make it a little bit prettier. So I still have the 1/2. And I would think about these as like all separate pieces multiplied together. So this is a fraction if I put the whole thing over 1, 2x if I put it over 1 as a fraction. Okay, so I have the 1/2 times, well this is a whole quantity to a negative exponent, and to make a negative exponent positive, we need to flip that whole quantity, right? The whole thing needs to move down, that's the whole base, to the denominator, and that would change the negative 1/2 to be a positive 1/2. But I have to have something still left on top, which would be a 1, times 2x over 1. And then, if I thought about what we do with fractions, right? When we multiply fractions, we multiply straight across, but we also maybe look for any common factors. This is all multiplied together that might cancel off. Well, wouldn't this 2 and this 2 cancel off? So I'd have the 1 times 1, the 2's canceled out because 1 was in the numerator and 1 was in the denominator, times the x on top. So I'd have x left on top, and then anything, as long as it's to a positive 1/2 power, would change back into 1 plus x squared all underneath the square root sign. And we would get this final answer. Trying to end in that notation we start with. It's not always doable to end in radical notation. If you start with radical notation, if the powers all of a sudden become like bigger, like the 3/2 power, the 5/2 power, it's maybe not as doable. But if it's 1/2, we would definitely be expecting you to switch. Okay? So speaking about switching, we're going to tag team. Hernie's going to come do 2 different examples to finish out chain rule part 1.
Let's get started. So let me give it in a little bit different notation just to make things confusing. So let's say we have d dx of 3x squared minus 4x all to the 4th power. Okay, so what I'm asking you to do then is take the derivative with respect to x of all of this. Okay, so I'm just telling you to take the derivative of it. Okay, our first step here is hopefully you recognize this is our inside function, and something to the 4th power is my outside function. Okay, so we got to take the derivative of the outside. So what I'm going to do is I'm going to take my 4 out front and then subtract 1 from my exponent. Okay, my inside part, remember, stays the same, so that's going to be my 3x squared minus 4x times then the derivative of the inside. This is going to make a 6x minus 4. And remember, you can't just leave it like that. We got to have the parentheses around the 6x minus 4. All right, but hopefully you recognize, so here I had d dx of something. I took the derivative of it. I did not write d dx of it anymore. I didn't write d dx equals. Okay. You're just going to go ahead. You don't even have to put an equal sign underneath it if you don't really want to. Okay, it's just working line by line. To clean this up, so there's a couple different things. Number one, you could just leave it like this. And then have a 3x squared minus 4x to the 3rd. Can be done. I know a lot of my answer keys will multiply this out. That's fine. You could even factor a 2 out of the 6x minus 4. So we don't really care which one of these you guys get to. There's no reason to do more work than you really need to. Okay? Like I said, or you could have factored out a 2. 4 times 2 then would be 8. If I took out a 2, I'd be left with 3x minus 2. And then 3x squared minus 4x to the third. So any really one of these three would be happy with.
Yeah, these are all called like equivalent forms. So these are all acceptable versions because they're all the same, representing the same thing. However, if you distribute and then you do this, now it's wrong. Because then it's 24x, the single term, minus 16 times all of this when it's supposed to be all of it. So if you're gonna do any like extra algebra, you better make sure to keep your grouping symbols where they need to be.
All right, next one. Let's do d dx. Okay, of the square root of 4x squared minus 9. All right, so on this one, recognize the square root really means the 1/2 power. Okay, so if I write d dx again, I'm going to put this all to the 1/2 power now. So 4x squared minus 9 to the 1/2. I really didn't do any math to this. I just kind of finagled it, made it in a different form. Okay, but I haven't done any math yet. Now I'm going to do the calculus step. I'm going to take the derivative with respect to x. Okay, so when I do that, you guys need to see that this is your inside part of your function. Something to the 1/2, that's my outside part. Okay, so I bring my exponent out front. And I subtract 1 from my exponent, so 1/2 minus 1 is going to be negative 1/2. Keeping in mind that the inside is going to stay the same. But then we have to multiply by the derivative of the inside, which would be 8x. Alright, you subtract, or bring your exponent out front. 4 times 2 is 8. Subtract 1 from your exponent, we get x to the first. The derivative of negative 9 is going to be 0, so we don't even need to write it. So here, since we don't, like that was just our derivative, we don't need parentheses there. Okay, so I'm going to rewrite this. Okay, so when I rewrite this, I see 1 over 2. So isn't that going to be 1 over 2? Here, this is a negative exponent, so I'm going to bring it down to the bottom and make it a positive exponent. 4x squared minus 9 to the positive 1/2 now. My 8x, there's no reason for that to be on bottom. It's not a fraction. It doesn't have any negative exponent. It's just going to be on top. So I don't really need to have times 1 there anymore. Okay. Couple things here. This is really 8 times x, and this is really 2 times everything else. Okay, so we can really reduce that 8 and the 2, making a 4. So we're going to have 4x on top. Okay, my denominator, we want to rewrite our answer in the same form that we started with. So the 1/2 power is just going to be a square root of 4x squared minus 9. Okay, just circle that as your answer then. Okay, don't write d dx equals, because that's going to now be wrong. If you wrote d dx, you're going to have to rewrite everything else that was in your first step. Of the square root of 4x squared minus 9 is going to equal all that. We don't need you to rewrite all that. Just circle this. Okay, but if you want to write something, you're going to have to write the entire beginning again. Okay.